Okay, so welcome back. We just introduced the basic definition of the Earth's atmosphere. And let's go ahead now and identify some atmospheric composition. Now, when we talk about constant gases, these are gases that are always present at the same proportion. So this is nitrogen, oxygen, and argon. Now, put in your notes that oxygen and nitrogen make up 99% of the atmosphere. Okay? And so when we go ahead and look at this pie chart, we see that oxygen makes up 20.95%, nitrogen is 78.08%, and we have other elements such as argon, carbon dioxide, water vapor, and other gases. Now notice that water vapor is the only one that has a range, so from 0 to 4%. Now, this is not a constant gas because it is a variable, okay, because it ranges. So there's certain places that have more water vapor than other places. And we can talk about those versus, ocean areas versus desert areas, more inland. Now, when we talk about variable gases, this means that it's different from place to place. So our water vapor, okay, so from here on out, water vapor is identified with a little arrow. So that's our water vapor. We have our carbon dioxide. We have our ozone is going to also have a variable, and carbon dioxide, sorry about that. And that makes up less than 1% of the atmosphere. So this is going to be very important. Okay, so variable gases obviously differ from place to place versus our constant gases that are going to always be consistent. Now, if we go ahead and look at water vapor, again, let's go ahead and look at the pie chart. So remember that it is a variable gas. We know that there's less water vapor over deserts, and there's going to be more water vapor over tropical forests and along the ocean, along the equator. Now, water vapor is great because it's going to absorb and store energy from the sun. Okay, and water vapor is going to be very influential when we talk about greenhouse gas, so the greenhouse effect. We know that warmer air can hold more water vapor, but we cannot see water vapor. Okay, so water vapor is something we cannot see, we can feel, and we need special lenses to view water vapor. So we're able to determine high areas of water vapor versus low areas of water vapor. Now, when we look at carbon dioxide, we know that there's 3.68 parts per million in the atmosphere. Now, this level is climbing dramatically. In fact, we hit a milestone in that we reached 400 parts per million of carbon dioxide in the last week. And so this is something that we'll talk about later. Carbon dioxide is absorbed by plants, which then under photosynthesis releases that carbon dioxide in the form of oxygen. So that's why it's important for us to be aware of practices of, cutting down vegetation, and just be aware that plants are going to be a very important process for taking carbon dioxide and producing oxygen. We know that carbon dioxide is a significant contributor to the greenhouse effect, and we've been seeing a steady increase of atmosphere since the mid-1800s. And that we've seen 50 parts per million increase in the atmosphere since 1958. Okay, and that's when really they started measuring amounts of carbon dioxide on Mauna Loa research station, because it was a good location away from cities out in the middle of the Pacific Ocean on the Big Island of Hawaii that was relatively high in elevation. Okay, so the last variable components of the atmosphere is going to be our particulates, and these are going to be small bodies of dust and pollen and even ash, volcanic dust, particulate matters that are going to be important because they can circulate the earth. They can stay suspended for a long period of time. They're nice and light, and they also attract water vapor. So that we can have water vapor form around these particulate matters and form water droplets. Okay, and we call that condensation nuclei. So we identified variable gases, constant gases, and particulates. So these are going to be the three elements that make up our atmosphere. Now, when we talk about the atmosphere, we have many different layers. Okay, so if we look at a column of the atmosphere, we can see that these layers are different, that they don't have the same percentage of gases throughout the entire column. Okay, so we know that the heavier gases are going to be closer towards the Earth's surface due to gravity, and the lighter gases are going to be at the higher levels, okay, into the atmosphere. So the atmosphere as a whole is about 10,000 kilometers thick, about 6,000 miles thick, but the mass majority of the atmosphere is going to be closer to the Earth's surface. Okay, so it's going to be, like I said, the most of those gases, the heavier gases, are going to be found closer to the Earth's surface due to gravity. Again, make sure that you can understand which ones are constant gases and which one are variable gases. Okay, so for the next part of the lecture, we're going to be talking about the layers of the atmosphere. Okay, so as I described in the last image, the layers of the atmosphere are going to be very different, and they're going to have very distinct thermal properties, and they are going to have very distinct purposes. Okay, and these thermal properties and purposes are going to be reflected upon the type of gases that we see and that exist in these particular layers. And so when you start thinking of the atmosphere, I want you to think upon layer upon layer upon layer, almost like the layers of an onion. And those layers are all of different width. Okay, and so the image that we see here on the right, this is looking at temperature of the atmosphere in degrees Celsius versus altitude. Okay, and so we're going to dissect this particular chart to identify the key elements of the atmosphere and break down the thermal properties. Okay, so we know that the atmosphere is this medium of constant gases, variable gases, and particulates. And we know that it's going to change. It's not homogeneous. It's not one layer that has the same proportion of gases. So we can break down these layers into 4 distinct layers, and these layers are going to have different thermal properties. And we're going to identify how these layers are going to change, and temperature is going to change as we increase with altitude. Okay, so the first layer that we're going to talk about is the troposphere. Now, the tropos, Greek, meaning that this is turning, mixing definition. So this is going to be the most active layer in the atmosphere, is the troposphere. This is the layer where we have weather. Okay, so it's the lowermost layer of the atmosphere, which lies between the Earth's surface and latitude of about 12 kilometers or 7.5 miles. Okay, this is my favorite layer. This is where we get the storms. This is where we have the hurricanes. We have our great snowstorms. This is the layer that we have weather. Okay, the turning and mixing, most active zone in the atmosphere. Okay, we also have a layer, so that's the troposphere. We have a layer that sits on top of the troposphere, and we identify as a tropopause. Now, as you are going to notice that when we start identifying layers, there's always going to be a layer and then there's going to be a pause. So such as the troposphere is the layer of mixing, and the tropopause is going to be a layer above the troposphere where there's no change in temperature, but there's change in altitude. So the tropopause it's marked by air temperature, and we see this at negative 70 degrees Fahrenheit. Okay, and it's an area that we identified. Now, the troposphere is warmed by the Earth's surface. Okay, so it's warmed by long wave radiation that's emitted from the Earth. Okay, so this is the air that starts to warm up by the radiation of the Earth. Now, the thickness varies from season and latitude. Okay, so the thickness of the troposphere is going to be directly linked to seasons and latitude. Now, the troposphere is the thickest at the equator, and it's going to be the thinnest at the poles. Okay, so lots of stuff going on here. We have this equatorial bulge that exists because of the Earth's spin, right? But we also, what's taking place at the equator is that's where the sun's energy, that's where it's focused, where we have a surplus of energy, okay? And we know that warmer air expands. And so we see this thickness variation that takes place along the equatorial region. So when we look at the thermal properties of the troposphere, okay, so we say that it's the primary layer where weather occurs, and 90% of the total mass of atoms within the atmosphere, okay, exists within the troposphere. And the temperature, here's the thermal property of the troposphere, it decreases with altitude at a constant rate. And this decrease is at 6.4 degrees Celsius per kilometer, okay? And for the troposphere, the number one source of heat, and this is going to be important, is going to be the Earth's surface in the form of long wave radiation. Okay, so let's go ahead and look at the troposphere as we put it on a chart looking at temperature and altitude. Okay, so we go ahead and identify that the troposphere decreases at a constant rate of 6.4 degrees Celsius every kilometer. And as you're moving up in altitude, it's going to be decreasing. So we can go ahead and draw our line in here. Okay, and we see at between 10 and 18 kilometers above the Earth's surface, we see there's a change. And that change is that we have this tropopause, where that temperature doesn't change. We identify just this key significant layer between the troposphere, where it's decreasing as we go up in altitude. And then we have this pause, where temperature doesn't change as you go through this layer, tropopause. Okay, so the next key layer in the atmosphere that sits above the tropopause is the stratosphere. Now, the stratosphere ranges from 7.5 to 31 miles in altitude, and this is the layer that contains the ozone. Okay, it contains the ozone layer. Tropopause is the boundary that sits above the troposphere where temperature reaches its highest point. Okay, so key elements on the stratosphere is that this is the layer where the ozone layer lives, and we know that we have the stratopause. So when we talk about thermal properties, we know that the stratosphere can be observed at 18 to 50 kilometers, okay, a range, remember, because that's going to have a seasonal variation, and it's home of the ozone layer. Now, the ozone layer is important for us because it absorbs the harmful rays of the sun, okay, and it filters it. Now, let's go ahead and talk a little bit more about ozone depletion. Now, ozone depletion takes place when we have refrigerant particles such as chlorofluorocarbons that are released and live in the stratosphere. And these CFCs react with our ozone that produces oxygen. Now, the more UV radiation that passes through this layer can harm us at the Earth's surface. So we start to see mutations in aquatic life, vegetation, and we see, as a result, skin cancer on humans. And we also see that ozone, areas where the ozone depletion is more severe, is going to be areas like Australia and Antarctica. Now, as a result of identifying these particles, CFCs, and how they were released and why they were manufactured for, in refrigerators and coolants and air conditioning. In 1987, there was actually a ban to phase out CFCs, and this is referred to as the Montreal Protocol. And this ban on CFCs actually has really helped with the depletion of the ozone layer. Okay, so remember, ozone is very important for us. We need the ozone layer, and CFCs deplete it, so it reacts. Now let's go ahead and look at the reaction that takes place here for ozone holes to become bigger, and what type of interaction is taking place. So we have our oxygen molecule, our O2, okay? And so with the shortwave radiation coming from the sun in the in the form of ultraviolet waves, it can break up